Section 13.2, Line Integrals, Video 6. Although we didn't officially or formally define a line integral in terms of a Riemann sum, you remember things that look like this: sum f xi star delta xi, way back in Calculus 1, and then we could do it for double integrals and triple integrals and line integrals. But although we didn't officially or formally define a line integral as a Riemann sum and taking a limit, if we did, this would be delta s. But we can also define a line integral along a curve with respect to x or with respect to y by going back to the Riemann sum approach and replacing delta s with delta x or delta y. And if we did that, we would get two different line integrals with respect to x and y. The line integral along C with respect to x is just the same line integral except with dx instead of ds. And similarly, with respect to y, the same line integral with dy instead of ds. Now, we will still attack it parametrically, so we have to know what to do with the differential, but that's pretty easy. Dx is equal to the derivative of the x function dt. That's really easy to see if you remember that x is equal to x of t, and then you take the derivative with respect to t and put x prime of t, and multiply both sides by dt. Same thing for dy. It would be replaced with y prime of t times dt. And frequently, these line integrals with respect to x and y are combined in a single problem like this one, where the integral sign is quote-unquote factored out, or you could redistribute it because integrals are preserved addition. So let's take a look at this one. Evaluate the line integral over the curve C of y squared dx plus x dy, where C is the line segment connecting the points -5, -3, and 0 to 2. As usual, the hardest part here is the parametrization, which really isn't too terribly hard. Let's go ahead and sketch this. -5, -3 is back here in quadrant 3. 0, 2 is on the positive y-axis. And if we connect them in that order, then we can parametrize this by saying x of t equals 1 minus t times the initial x-coordinate of -5 plus t times the terminal x-coordinate of 0. And if we simplify that, this disappears. Distribute the -5, we get 5t, and then 1 times -5 is -5. And then for our y parametrization, we can say 1 minus t times the initial y coordinate, which is -3. It's bothering me not having parentheses around this t. It looks like a function, and it's not. Plus t times the terminal y coordinate, which is 2. So if we simplify that, we have 2 t's here and then 3 t's here, because negative times negative is positive. So that's also 5t. And then -3 times 1 is -3. And again, our interval of t values using this parametrization is always 0 to 1. We could check it real quick. If we substitute 0, we get -5 and -3. If we substitute 1, we get 0 and we get 2. So it is the correct parametrization. So let's see what this integral is. We're integrating from 0 to 1. That's how we parametrize the line. Y is going to be replaced with 5t minus 3. So instead of y squared, we have 5t minus 3 squared. For dx, we take the derivative of the x function. So the derivative of the x function is 5 dt. Plus, replace this x with its function, so replace it with 5t minus 5, times dy. The derivative of the y function with respect to t is 5, so the dy will become 5 dt. And now we're back to a Calculus 1 problem. We can pull the dt out and just clean up this mess. In fact, I'm going to pull out the 5. Both of these have a 5, so I can factor it out. Just hope I don't forget it at the end, like I did in the previous video. If we square this, I can integrate that without squaring. but I get the feeling your intuition would probably say square it, so let's go that route. If we square this, we'll get 25t squared minus 30t plus 9, and then we have the plus 5t minus 5. So we still have the 5 on the outside of the integral from 0 to 1. 25t squared minus 25t plus 4 dt. Oh, goody fractions. So if we integrate this, we get 25 thirds t cubed minus 25 halves t squared plus 4t from 0 to 1. Well, the 0 will annihilate it, so we don't have to worry about that. Let's just substitute the 1. So substituting 1 will give us 5 times 25 thirds minus 25 halves plus 4. Common denominator is 6, so let's make that happen. Double both sides of this fraction, you get 50 over 6. Triple both sides here to get 75 over 6. And then rewrite 4 as 24 over 6. So 50 and 24 is 74, minus 75 is negative 1. So we get 5 times negative 1 6, which is negative 5/6. So yeah, line integrals with respect to x and y are pretty straightforward. You just have to know how to deal with the differentials, but basically replace each one with the derivative of their respective functions, dt. Let's take a look at another example in the next video.